All right. So before we start on the questions, a couple of administrative things. The conflict final exam is going to be Tuesday morning, the same day as the regular final exam, just 11 hours earlier. If for some reason you want or need to take the conflict exam, regardless of whether you have an official conflict, you're welcome to do so, provided we have enough space. There is a registration form linked from the regular course website. Please fill that out. Even if you filled out the other survey that said, hey, I need to take a conflict because of X, fill out the new form to let us know that you're actually coming to the conflict exam. Like I said, the space here is limited. I'm sort of betting on the hypothesis that most people would prefer to take the exam at 7 p.m. instead of at 8 a.m. But if that turns out to be wrong, then at some point the registration form is going to cut off. If you have it registered but you still need a conflict, send me email. Office hours are going to continue more or less indefinitely until the exam on Tuesday. In particular, I will have office hours in addition to Friday afternoon, which is normal, and tomorrow morning, which is normal. Thursday, at the time, we would normally be in this room, and Monday morning instead of Wednesday morning, because Wednesday is too late. Labs still meet tomorrow. Possibly they will turn into office hours on Friday by each of the TAs at the regular times. I'm still waiting for confirmation from the TAs that they're available. And I will be holding a review session this weekend, probably Sunday in the afternoon, but this will depend on when rooms are available, because I'm sure I'm not the only person running a review session over the weekend. And the one last thing, we're meeting to get all of homework 11 graded, so at least you'll be able to have the grades by the end of the week. And if things go as planned, you'll be able to pick up your homework 11s on Friday, or I can bring them to the review session over the weekend if you want to see your feedback on those. Any other administrative questions about the availability of the course staff or review sessions or anything like that for the remainder of the semester? Not about the exam itself. We can talk about that in a second. Yeah. 2 pages. Twice the midterm. So let me just briefly talk about the format for the final. In principle, there are 7 10-point questions. But chances are that, in fact, there'll be 5 sort of open format questions of the form: design an algorithm to do X and prove Y, and things along those lines, plus a long true, false, or multiple choice question. Similar to what was on last semester's final, which is essentially what you got as the list of last year's 20-point true-false question is essentially what you got in the practice problems a week ago. Okay. The breakdown that we would normally aim for if we had 7 It'll be 2 points from the midterm 1 material, 2 points from the midterm 2 material, and 3 questions from post midterm 2. So what this probably means in practice is you can expect there will be something where you need to prove something is NP hard. If I were breaking it down by this, you need something where you need to prove something is undecidable, and maybe some other question about Turing machines. For midterm 2, you can be pretty sure that there's going to be some sort of graph question, and there's going to be some sort of dynamic programming question. And for midterm 1, you can be pretty sure there's going to be something where you need to prove something is regular by building, a DFA or an NFA. And maybe, need to prove something is not regular by using some sort of fooling set argument. That's pretty much it. That's what we got time for. Okay. This gives you, I think, some idea about the relative distribution of topics across the points on the exam. So there's a little bit more than a third from the last chunk of the class, but the last chunk of the class is a little bit smaller, so it's cumulative, but with some more emphasis on the later stuff. You get 2 cheat sheets, both double-sided. Just like, is this the final exam? Do I have one of these? So there will be a list like this on the exam itself, listing a bunch of problems that you can assume are NP hard for purposes of proving things are NP hard. And there'll be a similar list of things that you can assume are undecidable for purposes of proving things are undecidable. Nevertheless, I strongly encourage you to make this list yourself by hand. Even if it doesn't make it into the 2 pages that you bring into the room, the act of actually writing these things down, and I want to emphasize, it works better if you write them by hand than if you type them, means that they'll be more accessible in your mind when it comes time to use them. At least for 473, what often happens with these cheat sheets, what a lot of students have told me is, once I wrote the cheat sheet, I never had to look at it. But because I wrote the cheat sheet, I didn't have to look at it. Right? Just the act of writing the stuff onto the cheat sheets, summarizing the semester's worth of material onto 4 pages, does a lot to organize the material in your head in a way that makes it easier to retrieve. Now, some people really do find it helpful to have this stuff in front of them. How do I solve recurrences again? Oh, yes, here's the 3 examples that give me how it works. What's the structure of a dynamic programming solution? What do I need to write down when I'm doing a graph algorithm? Vertices, edges, what problem am I solving? What are the running times of the basic algorithms? Whatever for search, topological sort, Dijkstra's algorithm, minimum spanning tree stuff, Bellman-Ford. It is sometimes useful to have those things in front of you on the cheat sheets so that you know that you don't have to memorize them. Again, though, by writing them down by hand, you'll hopefully find that you may remember them anyway without actually looking at the sheets. Are there any other questions about the structure of the exam or the coverage of topics or things like that? Okay. So with that, I'll open the floor to arbitrary questions. I'm not very good at predicting the weather, so you shouldn't ask me that. Don't feel constrained to ask me questions about specific problems that might show up on the final or might be practice on the final, because we'll have lots of opportunities for that. But that doesn't mean you should have not asked me those questions if you have them. So, yes, Marissa.
Can you walk through the...
Sure. Okay. So there was this question about fantastic Mr. Fox, who has to run through this obstacle course set up by Bogus, Bunsen, Bean, one fat, one short, one lean. So the rules are that you get this sequence of numbers. And Mr. Fox has to walk past each number, and at each spot he has to say either ding or ring. And I don't remember exactly which one was which, but you can think of it as I'm going to either say plus or minus. If he says one thing, then he gets the number of chickens that's written here. And if he says the other, he has to give that number of chickens back. Except that all the accounts are going to be settled at the very end. He doesn't count up chickens, actually carry around chickens at all. So you can think of this as I have to assign a plus or a minus to each of these numbers, with the restriction that I can't use the same thing 3 times in a row. Right? So I'm not allowed to say ring, 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 and I'm not allowed to say ding, ding, ding. Okay? And the score that I get is I sum up all the things that have pluses, and then I subtract off all the things that have minuses. Right? So in this case, 3 minus 4 plus 6 plus 2 plus 5 plus 7 plus 9 minus 2 plus 3 plus 8 is my score. Okay? So this is likely to be some sort of dynamic programming problem. Mostly I think that because there's some sequence where I make decisions early on and that affects what decisions are available to me later, which is similar to longest increasing subsequence and other things like that where we use dynamic programming. So I want to start by thinking of this as a recursive backtracking problem, where the question I have to ask is at the very beginning, should I say ring or ding? Should I say plus or minus? Should I take these points or should I give them away? And then based on what I've said, I don't know which of these two options is going to be the right one, but I'm going to try them both and recursively figure out what my reward is going to be if I say ring, recursively figure out what my reward is if I say ding. But there's this restriction that I can't say the same thing 3 times in a row. Okay? So somehow I have to remember when I jump into the middle, instead of making a few decisions, when I jump into the middle here, what I've said previously has an effect on what options I have available to me now. Right? So I have to keep track of enough information about my previous choices to be able to avoid this, these illegal patterns. So in particular, what that means is I need to know, have I just said 2 rings in a row? Have I just said 2 dings in a row? Because if I just said ring twice in a row, I can't say ring again. That option's no longer available to me. If I just said ding twice in a row, I can't say ding again. So what I'm going to remember is what's the last thing I said and how many times in a row did I say it? Right? So my the function that I want to compute is Well, one way to do this is like this. So this is the maximum score if we start at the ith number, and Mr. Fox just said whatever is stored in this previous thing, and he said it this many times in a row. Okay, so my initial call for this is going to look like this, I don't care, 0. Right? But for example, if I've already decided, if I've recursed my way down, and I've already decided that Mr. Fox should say plus minus, then the recursive call that I would make at this point is, what's the maximum score starting at the 5th position, 5. I just said minus, and I just said minus once in a row. Okay? All right. So here's my recurrence. Previous. Let me just call this R for R times in a row. R for row. Okay, so one possibility is that I've already gotten to the very end of the sequence of numbers. I've already made decisions about all n numbers, and at this point, I is n plus 1. Right? So if I is bigger than n, then there are no more numbers to think about. My reward is going to be 0. There's nothing else to do. Another possibility is that I've already said something twice in a row. If I've already said something twice in a row, I have to say the other thing. I have no choice. Okay? So I have one possibility that if previous equals plus and R equals 2, then I have to say minus. And so my reward is going to be whatever the negation of that number is. Here A is my input array. And then when I recurse, I'm going to start at the I plus 1th position. I just said minus, and I just said minus once in a row. Okay? Because before I said that minus, I said a plus. Another possibility is if the previous thing was a minus, and I've said minus twice in a row, then I have no choice. I have to add AI, and then I have to recurse by saying, you know, max score I plus 1 plus, but only once in a row. Okay. This is the situation that happened, or so the previous is plus and R equals 2. That's the situation that happens here. Because I said plus for these two numbers, I have to say minus for the next one. And then the more general setting is, well, I have two possibilities here. And I'm going to take the larger of those two. One is that I'm going to say minus. And one is that I'm going to say plus. And I don't know which one of these is the right choice, so I'm going to try them both. Now, what makes this a little bit more complicated now is that I have to decide what to put here. And that depends on what I said previously. Okay? So if I'm saying minus now and I said plus before, then I should put a 1 here. If I'm saying minus now and I said minus before, I should put R plus 1 here. Okay, so the way that I've actually defined the problem, now I have a few more cases to think about. But you could say, you know, if previous equals minus, then r plus 1, else 1, and here if previous equals plus, then r plus 1, else 1. Okay. Okay, so this is a natural point to stop and make sure that we actually understand what the recurrence is doing before we try or even think about how we would evaluate it efficiently. So let me stop and check, does this make sense? Okay. So now let's forget about foxes, let's forget about chickens, let's forget about scores, let's forget about what this thing means. If you bring 2 pens to your final exam, put one down and pick the other one up. Yes, I'm serious. You know, turn the page and come back 10 minutes later. You really want to use a different part of your brain for the next part of the dynamic programming thing. I need to figure out a data structure to use to memorize this function. Sorry? So a 2D array, well, wait, I've got 3 arguments. Okay, yeah. Yeah, I mean, really, I mean, the way that I've got it set up here, it looks like I should have a 3D array, but it's an n by 2 by 3 array. R could be 0, 1, or 2. Previous could be plus or minus. Right, so I have at most 6, in fact, really at most 5 interesting values to put here for any particular value of I. Okay? So I might as well just think of it as a 1D array where every element in that array is actually storing 5 numbers. Right? So I'm going to memorize this into a 1D array where you know, in each slot in the array, I'm going to store, you know, the various possibilities for max score, changing previous and R for a particular value of I. Okay? So when I evaluate the array, when I fill in this spot, I'm filling in a constant number of numbers instead of only one. But okay, that's fine. What order should I evaluate the array? Well, if I look at max score of I something something, that's this spot at column I, what other values does it depend on? Right, the one immediately to the right. Every max score I something something depends on max score I plus 1 something something. I mean, there are lots of cases. There's a constant number, you know, 8 cases, but it's a large number, but it's still only constant. But they all depend on just the spot immediately to the right. Which means when I evaluate this array, I want to do it from right to left. Another way to remember this is you start with the base cases, I is big, and you end with the value you actually care about, which I wrote down incorrectly, and that should be a 1. I is small. Okay? Whatever order of evaluation you end up with, it should start with the base cases and end with the target value you want. And now, how long does it actually take to do this evaluation? It's linear time because I have a linear number of things to fill in. Each one is 5 numbers, but okay, that's a constant. And for each of those 5 numbers, I have to do a constant amount of work. Now, remember, when you're memorizing, you should think of these things on the right not as recursive calls, but just array lookups. So if I want to fill in this spot in the array, I have to look in, I don't know, 4 or 5 other spots, all in column I plus 1. And that's it. So by doing a constant amount of work, I can compute the contents of column I from the contents of column I plus 1. And then finally, the thing I want to return is going to sit here in column 1, right in the middle. I haven't said anything. Make sense? So I think the hard part of this is actually here. What question do you want to ask when you jump in the middle of the problem? What recursive problem are you solving? What information do you need to keep to describe the choices you've made in the past? That's the previous in R. And what information do you need to specify the choices you have still left to make in the future? That's I. Right? And how do you phrase it in a way that it really does fall to the recursion fairy? So if you're going to hammer away at one thing for dynamic programming, the first thing to hammer away at is just being able to phrase the question, what problem do I want to solve recursively, cleanly? And then once you can see this, figuring out what the actual recurrence is hopefully that will be easier because you actually have a firm idea in your head what the recurrence is supposed to do. But there may be some feedback. You may try something here, try writing down a recurrence and realize, oh, this isn't quite working out. Maybe I need to make some slight changes to the function I'm evaluating and go back and try to figure out the recurrence. And then the stuff from going from the recurrence to the actual dynamic programming algorithm, hopefully that part is relatively mechanical. And the thing there to remember is, and I'm quite serious about recommending this, write down the recurrence, turn the page, solve some other problem on the exam, and then come back. So you're not distracted by actually thinking of this as a recursive call. This is not a recursive call, this is an array lookup. And the question is, how do I wrap a for loop around this to make sure that things are done in the right order? See this cartoon? That looks like an array with 5 things in each spot, and you evaluate from left to right. The order, yeah, this is enough detail to figure out what you mean. I'm sorry?
I write down the solution.
But it's a 1D array of what? It's not a 1D array, nor if you just say a 1D array, we assume you mean a 1D array of numbers. It's not a 1D array of numbers. It's a 1D array of where each element is, a small constant number of things. You need to actually say that. Yeah?
What are we going to do in theory 2?
What are we going to do in theory 2? I especially like the pronoun in that question. Let's see. So there's some stuff that is more advanced versions of the things that we've seen in this class, or maybe spending a little bit more detail, getting a little bit more mastery practice. In particular, we'll spend a little bit of time looking at proving things are NP hard in a bit more detail, with a bit more practice. We'll spend some more time talking about more interesting versions of dynamic programming. So you can do dynamic we briefly touched on doing dynamic programming over with a DAG using topological sort instead of just over an array. There are some other nice tricks that you can play with dynamic programming. If your problem has enough structure, you can sometimes shave off a factor of n or more by exploiting some structure in the memoization table itself. so that, in particular, you don't actually have to compute at all. Right? Those are some nice things to know. We're going to talk a bit about randomized algorithms, starting with the sort of base. The most fundamental one is randomized quicksort. Why does randomized quicksort run in log n in time with high probability? What does high probability mean? And a little bit of time talking about amortized analysis, which is you have a data structure, and in 225, generally speaking, you want to design your data structure in a way so that every individual operation you do is fast. But most of the time, that's actually more than you need. What you actually want is to know that if I do a long series of operations, the total time is small. It's okay if I occasionally have an expensive operation, as long as it doesn't happen too often. And amortized analysis gives you a way of talking about this in a formal way. So we'll talk about other versions of balanced binary trees as a sort of warm-up for this. And then the big thing for both of these is I'll spend some time talking about hashing. You actually need both of these to talk about hashing correctly. What is a good hash function? Why is it good? How do you build hash tables? How do you analyze how good a hash function is? How do you analyze how good a collision strategy is? What should you use in practice that you probably didn't see in 225? There's really been enormous advances in hashing algorithms since the stuff that you saw in 125 and 225 or in your ECE classes that was basically all done in the 60s. We know quite a bit more than, for example, Knuth did when he wrote about hashing. So if you just do what Knuth said, you're not doing the right thing anymore. Then stepping back, talking about graph algorithms, we won't be doing minimum spanning trees and shortest paths, but we'll do the next sort of fundamental graph problem, which is really a pair of problems that are interrelated, called the maximum flow and minimum cut problem. Essentially, you want to think of it as I've got this system of pipes where every pipe can carry so much water per second. I'm going to inject water into the system at one point, and I'm going to pull it out at the other. How much water can I push through the system all at once? How many megabytes can I move from that data center to this laptop? How many train cars full of coal can I move from Moscow to Berlin? And then the minimum cut problem is if I now take this network and I destroy some of the pipes, I can make sure that you can't get any water from one point to the other. What's the minimum amount of destruction I need to separate the graph into two pieces? And these things get used in a lot of different kinds of problems can be phrased as flow and cut problems. So there's various how do I assign final exams to rooms in a way that makes sure that no room gets used more than once and exams get scheduled at different times. Lots of scheduling and assignment and rounding matrices. There's a bunch of different problems that fall under this category. It's actually a much richer set of problems than what you can get from shortest paths of minimum spanning trees. And then this sort of naturally flows into linear programming, which is another big hammer-like dynamic programming that we're not really going to spend much time talking about algorithms. It's more going to be about modeling. This is an off-the-shelf thing that people have won Nobel Prizes for, that economists like to use all the time. But again, you just have some linear constraints on some variables, and you want to optimize some linear function. Shortest paths are an example of this. Minimum spanning trees are an example of this. Maximum flows are an example of this. There's a much more general way of formulating these things. And then finally, if there's time, we'll close the loop by talking about approximation algorithms, where you've got a problem that's NP hard, so there's no hope of getting an exact algorithm that runs in polynomial time. But maybe you can, in polynomial time, compute a solution that's at most 50% worse than the actual optimum solution. This is the case for the traveling salesman problem, for example. There's a fairly fast algorithm to get a traveling salesman tour that's at most 50% longer than the minimum and than the optimum. And the sort of approximation stuff sometimes relies on dynamic programming, sometimes relies on randomization, sometimes relies on linear programming, sometimes relies on randomized rounding of linear programming. You know, it's the sort of combinations of these things, so it's a nice thing to sort of end on. This is all tentative, and I'm aware, staring at this list, that I have 15 weeks. And that's a lot to do in only 15 weeks, so we may or may not get to all of it. The only piece of this that I don't normally do in 573 is this, and maybe I don't always have time for approximation algorithms. So essentially, this is going to look like 573, except we don't have to spend as much time talking about dynamic programming because you just saw it here. We don't have to spend as much time reviewing graph algorithms because you just saw it here. And I'm hoping actually that when we, that there'll be enough, I'll have enough time in the schedule when we're talking about hashing to talk about something called streaming algorithms, where you have a box that's hooked on, say, something on the backbone of the internet, and you want to learn something interesting about the traffic that goes by. But you have a small box. It has to, route things in milliseconds. You've got maybe a couple of megabytes of memory, and you're going to see a terabyte of data every hour. Do something interesting, which now starts to feed off into the realm of big data and machine learning and other stuff like that. So I'm hoping to be able to get to this because it's cool. We'll see. Yeah.
How do you predict that course load will be?
About the same. Modulo a couple of things. This course is required. Everybody has to take this course. That means we have to aim the course so that we can reasonably expect every computer science major to do reasonably well, at least well enough to pass. This course is an elective. Right? This is an elective. This is also going to have grad students in it. Okay, so in terms of homework, in terms of the number of homework problems, about the same. Maybe it'll be 5 problems every 2 weeks instead of 3 problems a week. Maybe we'll have only 1 midterm instead of 2. So, but it'll be harder. Again, there's a bit of calibration going on here. I've never taught an elective undergraduate course. I don't actually know what that means. I have this idea in my head, which is probably completely wrong. Part of the reason why I think this is likely to be harder is, that's the things that make the material worth teaching are that they are somewhat, some pieces of them are quite counterintuitive. It takes a bit of time to wrap your head around what a flow actually is. It takes time to understand what amortized analysis actually means. Right? It's a conceptual barrier to get over it. And the whole point of teaching this material is that once you get past that conceptual hurdle you get a really powerful tool that's actually incredibly useful. Right? But this goes hand in hand. It's hard because it's useful. It's useful because it's hard. Right? The one thing that I actually hope that this course satisfies, one thing that I find a little bit unfortunate about the theory revision. This department, I'm speaking now, of computer science, because I don't really have that much experience with computer engineering. The computer science department is actually well known. We have a very, very strong reputation among alumni and among employers for giving students a solid theoretical grounding. Not just, oh, you do these fancy theory things that you prove stuff that doesn't have any use in the real world, but we actually ground students in the theory that they actually go and use, right? And to much greater extent than most other departments in the US. So there are a couple of other places like CMU, MIT, maybe Berkeley, Princeton, maybe one or two others that I'm not thinking of, where the required algorithm sequence has as much depth as 473 did. We've lost that now. We've lost the required algorithm sequence doesn't have the same depth as it used to. What I'm hoping this course does is say, well, look, the required curriculum, it doesn't go as far as we used to, but there's more available. And again, my choice of topics here is based on what I think is useful, not what I think is, pretty or mathematically elegant, but really what I think people will use, what people will value going out, regardless of whether you want to go into computer science research or go into industry. And so what I'm hoping is this will be something that recruiters will look for. So the short version of how I sell this class is 374 is the algorithms class you take if you want a degree. 473 will be the algorithms course you take if you want a job. That's putting it a little bit too harshly. But every so often I get to brag. So, yeah.
Outside of theoretical.
So the reason why NP hardness is useful is not so much because, especially if you're going into industry, you're never actually going to be called on to prove that something is NP hard. If you're doing research outside, in industry, you're actually more likely to want to prove something is NP hard outside of theoretical computer science than in. Because within theoretical computer science, we've pretty much mapped out the landscape. But outside, when you're facing a brand new problem, it's sort of natural to wonder, can I actually solve this thing exactly? And what having this NP hardness toolbox allows you to do is to say, well, no, this kind of looks like a minimum, a traveling salesman problem, or this kind of looks like a graph coloring problem. Sure enough, I can reduce graph coloring to it. There is no hope of getting a general purpose solution to this. And that steers you away from an entire mindset of how to solve the problem. You have to steer yourself towards exploiting some structure in the data or realizing that you can't get the optimum solution and so accepting something that is reasonably close to optimum. And I think the same is true, out in the real world. In the real world, you say most problems are actually NP hard. Most interesting problems, I should say, are NP hard. Most problems that real-world programmers face tend to be of the order of, I need to make this, there's an enormous skill in making user interfaces work and be consistent. There's an enormous skill in making things actually accessible, making things actually, even the basic stuff like for loops actually be efficient when you actually run them. I'm declaring those to be a different kind of problem that I'm talking about. But any kind of interesting problem where you're allocating resources or optimizing something, most of the time that turns out to be NP hard. And it's nice to have the tools to say, stop trying to solve it exactly. Change the problem, change the goal, allow yourself to work most of the time, understand something about the internals of the data, but looking for a complete, efficient, general-purpose solution is just not going to happen, right? And I think more than anything else, what we're trying to get across by exposing you to this NP hardness stuff, and also to the undecidability stuff, is a real, not just a sort of, I read Wikipedia level knowledge that some things are hard, but some intuition about the kinds of things that are hard versus with dynamic programming or graph algorithms, the kinds of things that are doable quickly. So, will you ever prove anything is NP hard again for the rest of your life? No, you won't. I'm probably wrong for one of you. Right. Probably there is someone in this room other than me who will at some point in their future actually prove something is NP hard and not just from taking this class. But most of you won't. Nevertheless, I think having that intuition is useful. Yeah.
How do you see this class, the SP74, evolving?
How do I see it evolving?
Whether it be in terms of like the syllabus itself is changing?
So, I mean, I've tried very hard to keep notes about what's worked and what hasn't, and I'm certainly open to hearing your opinions on this. We are scared, right? You know, this is a difficult class to teach to 70 people. Right? It's very tightly constrained because we're combining two classes, that each of which used to be 3 hours long, and having to throw material out. And over again, I've discovered, no, really, I have to be extraordinarily disciplined about what I talk about, or I'm going to run out of time for something important. So from the point of view of actually doing the instruction, this is not easy. From the point of view of actually doing the administration, it's even scarier because the people who are going to be teaching this class, we haven't taught 400 student classes before. We've all taught 200 student classes before, and we understand kind of how that works. But every factor of 2 matters. Teaching a 50 student class is different from teaching 100. Teaching 100 is different from teaching 200. The largest class I've ever taught had 300 students in it, and it was a disaster. Really, just, no, don't do that, right? Don't have the lecture in a room that will hold 200 and have a 100-seat room as an overflow. It doesn't work, because even if I'm, you know, my pretty face is up here on the screen, everyone who's in here is talking, reading the DI, playing solitaire, reading Facebook, because no one, you know, they're disconnected. So I can't see them from the other room. So we're not going to do that. The lectures are going to be over in ECE. Part of the question is, you know, simple things like how do we run office hours? You see how crowded the office hours are now. If you've ever been next to my office Monday at 1, when Yipu is running office hours for the current 473, it's a mosh pit. Right? There are people 20 feet away from the room, standing room only, trying to, you know, oh, why doesn't, you know, because for exactly the same reason that people come to office hours here. That's at a class with 200 students. So we actually have a room over in Everett reserved for, I think it's 36 hours a week for office hours specifically for 374 and 173. And that's going to just be a permanent feature. But even there's going to be some load balancing. Are we going to have to tell people only go to the office hours of your TA? right? If I'm teaching the class, that room is only going to hold 50 people. If 200 people want to come to my office hours, what do I do? How do we grade homeworks? With this class, we've been able to keep up with it by saying, okay, we're going to give all of problem 1 to you. We're going to have this simplified grading scheme. If you have any questions, get in touch with us. There's a wiki going on in the background where we actually track every homework problem and whose hands it's in. But now there's going to be 5 times as much homework. Can't just give it to one person and expect it to be done in 4 days. 20 maybe, but not 4. So we don't know how that's going to work either. And there's a learning curve for every instructor of, you know, maybe we need to have online quizzes, but we don't know what those are going to be yet. Maybe we want to emphasize, you know, topic A over topic B, but we don't know exactly what to emphasize on topic A to actually make it useful, interesting. So it's still, you know, my hope is that over time it's going to evolve into something that's actually fairly stable and fairly comfortable, but I think that's going to take a couple of years. And you know, my hope and for, you know, in terms of topical coverage, the way it will evolve, the sort of guiding principle that I try to run with is at some level, I don't care what you know. What I care about is what you can do. But what that means is that we need to set up the environment in a way that helps you gain the skill to be able to do those things. I would like you to be able to prove that a problem is NP-hard. That's a skill, as opposed to being able to parrot back the definition of NP-hard. That's a piece of trivia. You can win a beer at Murphy's by knowing the definition of NP-hard, but you can kind of get that by reading Wikipedia. It's the skill you can't exactly get by reading Wikipedia. I'd like you to be able to develop dynamic programming algorithms, not just know what dynamic programming is. And in particular, the skills that I would like the class to encourage to develop are the ones that are actually going to be useful in other 400-level classes or out on the job or out in grad school, in whatever field of grad school you're using or you're studying. Again, not just the ones that are, you know, mathematically prettiest, but the ones that are actually going to be most useful for you. Not everybody has this opinion. Different people have different emphasis and different goals for what they want the course to be, and so there's going to be some negotiation. And probably at steady state, the course is going to change every semester depending on who's teaching it. I don't know, I hope that answered the question. Yeah.
I was going to say, are you going to get a whole board of TAs for next year?
Yeah, the plan is to have 8 TAs and somewhere between 15 and 20 undergrads. Right now, we have 5 TAs assigned to the course. There's this problem that we have 374, which needs 8 TAs, and the old 473, which needs 2 TAs, and the new 473, which needs either 1 or 2, depending on how many people register. That's a total of 14, or that's a total of 12 TAs that we need for these theory classes. There are 9 theory students who don't have RA-ships or fellowships. So I'm wandering over to ECE saying, hey, you promised us a TA. I'm wandering over to math saying, so I understand that you have less need for TAs in the spring. We have more. So yeah, that's going to be, and it's also going to be interesting hiring the undergrads, because not that many undergrads have taken 374 yet. So if you are interested in helping to grade, helping to run labs, helping to steer the direction of the course, please talk to me or to Chandra or to Lenny. Chandra and Lenny are going to be the ones actually teaching it. I'm going to be kind of helping in the background, but not as much. Yeah?
Can you tell us what the requirements for how long you have to do this class
So at steady state, normally what I would recommend is at least an A minus. Right now, we're not in steady state. So I think it's just as important to have people who are interested and who have some insights into how people struggle with the material, who can help the students who struggle with the material. One of the problems with hiring only students who get A's is that generally speaking, the students who don't get A's didn't struggle as much with the material. And that makes it harder to communicate with the students who do struggle with the material. So at this point, I have to say, if you're interested, talk to us. Right? This is a learning curve for us. I mean, we're sort of forced into letting go of our intellectual snobbery just because of the raw numbers. We just can't afford to be as elitist as we have in the past, and that's probably a good thing. Yeah.
So did you say different people are going to be people?
Yeah.
Because that feels like a 241 sort of.
Well,
Sorry.
No. That's an absolutely fair fair criticism. The alternative to we have somebody new teaching it every semester is the same person teaches it every semester. And so far, we haven't been able to convince the tenure track faculty that really you should teach a 400 student class every semester. We have even the instructional faculty that's their job full time. Lawrence teaches 241, that's his job. Cinda teaches 225, that's her job. Wade teaches 105, that's his job. They're pushing back with the increasing size of the classes, which is why in 225, now it's not Cinda's job, it's Cinda and Anna's job. Because Cinda says, no, I'm not going to teach 700 students a semester. Good, right? The other thing that is a bit uncomfortable about having only one person teach the class is what if somebody gets hit by a bus? What if somebody is sick? What if somebody has a death in the family? What if things happen? And if there's one person and that's the only person who can teach the class, we have had discussions about this. What happens to 241 if Lawrence gets sick? So what we're trying to do over the next several years is build up a set of about 6 or 7 people who can rotate through regularly. And so if somebody needs to go on sabbatical, okay, fine, we'll skip ahead. But if somebody gets sick, okay, fine, we have somebody who's taught the class and who can act as a backup. Right? I think that's actually a much healthier model than just having one person all the time. At the same time, I'm aware that it's very easy to take a course and go, oh, this is totally wrong, I'm going to do it my way. And unless you're Brighton, that's usually a disaster, right? For Brighton, somehow it wasn't a disaster. I think he has a halo. I just hope his company sells for a lot of money and then he comes back. So, yeah, there'll be people in the background going, no, really, you need to, some flexibility, but really, you need to do these things. That will be my job, I guess. In particular, we're a little bit nervous about the fact that about 1 out of 4 of the instructors for this class are going to be from ECE. Because it's a cross-listed course. This is going to be CS 374 and ECE 374 because it's required for CE students. as far as I know, none of the CE faculty have ever taught a theoretical computer science course before. They're going to learn, right? So next semester is Chandra and Lenny. Right now, planned for the fall 2015 is Nitin Vaidya with Chandra. For spring 2015, spring 2016, Mahesh Vishwanathan wanted to teach it himself. He's taught both 373 and 473, so he'd actually prefer not to have fights with other people. I'll just do it myself. Okay. At some point, I think Sayan Mitra has expressed interest in teaching this class. I don't know how that's going to work because I can walk down the hallway and see the other people. I can hear the students talking about how the other instructors are going to do. There are these people from some other building that I kind of know, but I don't know how well they're going to do. This would not be the environment to tell me how they're going to do, by the way. Yeah.
Why aren't you teaching it?
This is my third semester in a row of teaching undergraduate algorithms. Next semester will be my fourth semester in a row teaching undergraduate algorithms. I'd like a break. I do expect to teach this class every 3 or 4 semesters. But I want to, it's been a lot of work developing it. I'd like to do something a little bit easier for a while before jumping back into the parting the Red Sea kind of class. Yeah.
Why don't you think similar to what the math class that you would have 2 completely separate courses?
So at the moment, the way that we're running this is it's up to the people teaching the class how they want to organize it. There are good and bad aspects of both of these. The nice aspect of having a combined class is that you share resources. You have one set of homeworks, one set of exams, one set of lectures. We may find that it's actually, you've all had much larger classes than I have, more recently than I have. So I'll just ask you, if you're given the choice between the better of the 2 lecturers is going to have one 400 student lecture versus everybody gets a 200-person lecture, but somebody, every instructor has to give a lecture. What do you do? Well, that's up to the instructors. So 173 this semester, Margaret and Madhu are each teaching essentially an independent class. Different homeworks, different exam structures, different final, everything is different. It's just 2 sections of 173, right? Because they have very strong opinions about what the right thing to do, very strong opinions about what they wanted to try. They said, okay, fine, you take 300, I'll take the other 300, and we'll try them both. And probably that will happen for 374 at some point. My wife is teaching Calculus 2 with Scott Algren. So she has 2 sections and he has 1. And so there are 3 lectures and 15 discussion sections. But they combine homeworks and they combine exams. And again, that seems to work out reasonably well for them. Lenny and Chandra decided they just wanted to have 1 lecture, because it's probably going to be videotaped anyway, and so people have the freedom to watch the lectures whenever they want. Not clear, whether, is there enough benefit to just having multiple times when the lecture is given? I don't know. It doesn't really save anything as far as the course administration goes. So, again, I just don't know. I haven't ever co-taught a class with multiple sections. So I don't have anything to, any judgment, any basis for comparison. And part of the reason why I don't worry about that quite so much is I actually think the discussion sections and the homeworks are more important than the lecture. But yeah.
On the final,
Yeah.
if there are any multiple choice questions, will it be similar?
Yeah. If there are true-false questions, I suspect if they're true-false questions, we're going to be nice and just say you get a 0 or 1 and not have negative scores. For larger multiple-choice questions, I think there's some value in saying I don't know versus picking the wrong thing. So, I may change my mind later, but right now my tendency is we'll probably not take off. We'll not give negative scores for the wrong answers on those things.
Just out of curiosity, what?
Okay, so right now, the other theory classes are all 500 level. So every spring there's a class on complexity theory, which sort of starts with P and NP as day 1, and then there are more larger classes of problems that are even harder. There are other kinds of ways of looking at the complexity of a particular kind of computation. There are questions like, okay, suppose I want to do interactive computation. How much data do we have to communicate to each other in order to agree on something? If I want to convince you that something is probably true, can we agree on a small number of questions that you can ask me? And surprisingly, the answer is yes. There's, on the algorithm side, there's a regular class on randomized algorithms, which starts with the stuff that we're going to do in 473. There's a regular class on approximation algorithms, which starts with the stuff that we do in 473. Next fall, I'm probably teaching an advanced class on data structures, which starts with the data structure stuff we do in 473. Sometimes we have other special topics things. So this semester, for example, Chandra's teaching a class on algorithms and machine learning. We've had optimization classes before. We've had classes on algorithms for big data. We've had classes on computational geometry. It varies over time. The formal methods group is planning to revive 475, which used to be the standard automata theory formal languages class that turned into 373 10 years ago. But it's probably not just going to be an automata theory class. They want to do more interesting things with it related to logic and so forth. The formal methods people also do some formal verification programming language semantics type of classes, which depending on what university you're at, fall under theory. With all of these, the interesting thing is that with the special topics algorithms classes, even though they're 500 level theory classes, first, there are always undergrads taking them. And second, a majority of the students are not theory students because we don't have that, we've got 350 graduate students, of which a dozen study theory. So they're definitely theory classes, but on the other hand, we try to aim them again at, approximation algorithms are really useful in things like networking and distributed systems and compilers and so on. So we try to hit the points that, again, they can take back to their own research areas and use there. Yeah?
The advanced data structures class.
That is a very interesting question. So, given the choice I prefer to teach in a room with a blackboard. If I want the videos to be available online, I have to teach in a room with a camera. I don't know of any room on campus that has both of these things. Do you?
There's a question. Why on earth doesn't
Wait, let me get this straight. The ECE building doesn't have cameras?
well, I mean, all the ECU buildings have blackboards. All the
They don't record because they can't?
They don't have a camera.
Oh. Well, there are a number of four-letter words going through my head right now. I'm going to go out on a limb and guess that that will be fixed at some point. Yeah.
I'm pretty sure some of them do have cameras, they just like aren't working yet. Like,
Okay.
They don't have all the AV stuff figured out. Some of them might not have them.
Yeah, I have to imagine they're just not done. I mean, everybody moved into the building before it was done. I mean, if I understand correctly, the beginning of the semester, there was one sort of working projector on one side, and there were no curtains on the windows, and there are no left-handed desks, and, you're teaching a 400-student class. About 40 of your students are going to be left-handed. Maybe you should have some left-handed desks. Yeah. Yeah.
I took the instructors like a year.
Yeah, it's been a while since I have.
Seeing if I could take that course that I wanted to.
Well, okay, there are two parts to your question. One, will the class be in a room where we can actually broadcast it, right? One thing that I would check out, the advanced data structures course that I teach is based on a class that's taught at MIT. A lot of the material, I spin it myself, but the basic outline is based on a class that Eric Demain developed at MIT. His lectures may be online now. So a lot of MIT classes, they recorded stuff and everything is freely available. I don't know if his lectures for this are actually available, but you could check that out. So there are two pieces of this. One, will it be in a room that will allow me to record the lectures at all? Two, will the university allow people who are not on campus, who don't have net IDs, to watch the videos? The official policy of the university has always been videos are restricted to people with actual net IDs. But I observed this morning, as I was fixing the lecture page, that sitting in Flying Machine, I could watch my own videos. So they may not be enforcing that policy anymore. So that's a question I don't have an answer to, is if the lectures are recorded, will they be available off campus? I would like to think that the answer is yes. In fact, if I ruled the world and bunnies were made of chocolate and all that crap, every lecture given by every instructor on campus, every semester, would be uploaded to YouTube automatically. Full stop. Every lecture, every class, every room. Because the lectures are not what we sell. The lectures are what we use to sell what we sell. right? So, but when I've asked about this in the past, I was told either no or don't ask, right? I will point out that there are YouTube videos on the web that 225 TAs have prepared for like review stuff. They didn't ask for permission. I was very smart. We're over time, and I do have to be back in my office in 10 minutes, but if there's another quick question, I'm happy to answer. Yeah.
For grades going into the midterm, is there ways to do that individually?
I'm sorry, for?
For grades going into the midterm, get an idea of what our grades are.
I think the best way to answer that question is how you did on the exams is probably a better predictor than anything else. And then, you know, bump up a little if you've been doing really well on the homework, bump down a little bit if you haven't been doing as well on the homework. But really, the exams tell most of the story.
I guess I don't know.
I'm happy to talk to you one-on-one, but all right. Thanks.